What was my motivation for making a visible light oscilloscope probe? Originally, I wanted to measure and calibrate the shutter speed on my film cameras by putting shining a light in the lens and putting a sensor behind it and measuring the shutter times. Then I thought about it and I go, well, I could use this to measure the flash and pre-flashes from my camera strobes. Then this year I've been watching a lot of Big Clive videos about lighting technology, and that made me interested in investigating further the relationship of voltage, current, and flicker waveforms emitted by various lights. And then I wanted to be able to measure the flicker and lighting that doesn't work well with video, and Dave Jones recently had a couple of videos about this. So before starting any design, you need a clear set of goals. These goals, you may modify them as you work and discover you can't achieve them, but you need to have a goal to start with. So my first goal was to use a sensor with a wavelength sensitivity as close as possible to the human eye, because I wanted to investigate the lighting effects on visible light cameras and flicker for humans. And the problem is most sensors have their peak sensitivity in the infrared, not in the visible light range. I wanted to make a no offset adjustment design, so 0 light in with 0 volts out, and no trim pots would be required for it, and that would also keep production costs down if I decide to produce this later. I want to be able to do a dynamic range from ambient room lighting up to photo flashes, which are very bright. I want to have a fast rise and fall time, so I can measure the response of high-speed switching in LED lights and measure the light waveforms produced by camera flashes. Ideally, I'd like to be able to power it with a single battery. I'd like to have a 50 ohm out impedance so I can drive long coax cables in case I want to keep the sensor a long way away from the scope. And a simple bill of materials for low cost and easy construction. So after looking, it took me a while, but I found this Osram phototransistor that has its peak response in the visible. If we look over here at these on the left, this is a graph of the wavelength on the in nanometers on the x-axis and relative response from 0 to 100% on the y-axis. This inner curve is the average response of the human eye, where it peaks in the green, and then this bigger curve on the outside is the response of this phototransistor. Now this phototransistor has a wider response than the human eye, but the peak sensitivity is still in the visible. Whereas almost every other sensor you find is going to have a peak sensitivity over here in the infrared, and the visible will be more in the tail. Now, if you look at an infrared remote, they mostly use gallium arsenide IR LEDs, and they emit around 850 nanometers. And so this still has 33% response at that frequency, at that wavelength. And so it will be useful for measuring the response of remote controls. Now this graph on the right shows the sensor's angular sensitivity. So here 1 is normalized to straight on, and you can see as you go off at an angle it drops off, and at 80 degrees we're only down to about 50%. So it's going to pick up a lot from the side, so it'll need to be shielded if we want it more directional. And the key thing about it is its leakage current is more than an order of magnitude below the signal current. So the photosensor itself will not generate inherent offset. Then looking for an op-amp, after looking, I just found this one and decided to use it. It's got a very tiny 3 microvolt maximum offset voltage, and in fact it's typically much smaller. It's got a 14 megahertz gain bandwidth product, which is very fast for a zero drift op-amp. Most op-amps in this class are in the hundreds or tens to hundreds of kilohertz and do not respond this quickly. And it's got a very wide supply range, so it'll work fine off a battery. So this is the circuit I came up with after some work. Let's first look at the active devices. First is the SFH3310 phototransistor. The spec sheet says a VCE max of 5.5. In my experimentation, I discovered 3.5 is probably the largest voltage you should use on it. And if 5 volts is on it and you hit it with a bright light, it latches and it doesn't work anymore until you turn it off and on. Now the range of currents it puts out over for the lights I want to measure is about 10 nanoamps to 20 microamps. And although the dark current is spec'd to be less than 3 nanoamps, it's really on the order of 100 picoamps, and its capacitance is on the order of about 3 picofarads. Again, here's the op-amp. Slew rate's 20 volts per microsecond, but that's into 36 volts and a gain of 1. I'm not using it there. 1.7 milliamps per stage. Offset voltage is really typically below 400 nanovolts, very small. The input current spec'd at plus or minus 300 picoamps, and it's all MOSFET op-amps. That's dominated by the input protection ESD diode leakage. And so there's really no way to compensate for that because you don't know what you're going to get. And the noise is spec'd very low, but only below 1 kilohertz. And it will drive up to 65 milliamps into a short circuit. Then here, this band gap voltage reference I'm using needs at least 120 microamps through it, and 30 milliamps is the maximum current it can sustain. And the total capacitance across it needs to be below 10 microfarads. And lastly, I used an Algas LED for its low on voltage. So if we look here at the front part of the circuit, here's the +9, the -9, and then there's a reference rail here about 2.5 volts above the negative rail. And the current through this resistor and LED keeps this band gap reference biased. Now you can pick this resistor here. I'm using 2.2K for a very long battery life, but the LED's on very dimly. You can light the LED up very brightly, but then you're going to triple the current consumption of this thing, but you get a nice bright LED. It's kind of up to you. You can change this resistor anywhere this range works. So here's the phototransistor, and the phototransistor essentially acts like a current source whose amplitude is proportional to the incoming light intensity. So if you look here, when light hits it, it pulls current down, which causes the output voltage of this stage to go up, the output voltage of the next stage to go up even more, and the output voltage of this last stage to go up even more. Now this first stage is a classic transimpedance amplifier configuration. It keeps, because of this rail, it keeps 2.5 volts across this transistor. And this C7 capacitor is required to stabilize this amplifier because the capacitance of this phototransistor creates a pole that makes this op-amp slightly unstable. And so you have to add this capacitor here. This is pretty much typical in any transimpedance amplifier. Now what's interesting is the models for these were pretty much useless, the op-amps useless for determining the compensation capacitors I used, which doesn't surprise me. Most models suck. So I actually had to do this on the bench with some experimentation. Now this next stage is just a voltage amplifier with a gain of 12, and then this last stage is a voltage amplifier of gain of 12. And I reached these gains by experimenting. This was the one that gave me the best sensitivity range and rise times and things I wanted. If you put all that gain in this stage, it would be very slow because the gain bandwidth product would cause the bandwidth of this amplifier to drop as you up the gain. Now here, the C8 compensation capacitor is required because for very large, fast signals, this last stage here actually becomes slew rate limited, and it likes to ring when it comes out of slewing. And so you have to add this compensation capacitor to tone that down. And there's a trade-off between the amount of ringing you allow and the slew rate. And then here, this is the ground reference for the output, and I'll talk about this in a minute. And if we look back here, you see 48 ohms output impedance because I have 224 ohms, and this is essentially 0 ohms and 0 ohms because they're inside the feedback loop. So I'm getting my back terminated 48 ohms output, or close to 50 ohm output impedance I wanted. Now the issue comes when you want to drive a 50 ohm load. Now if you want to put 2 volts into a 50 ohm load, that's 40 milliamps. Now these op amps at 40 milliamps, they're going to drop a couple volts below the rail. So here these graphs from its spec sheet are specified for 36 volts. I'm using 9 volts, and so excuse me. I'm going to get a little more drop at 9 volts than the spec sheet says. Now, so if you did, but the reason I need this here to sync the current is just at 2 volts across it, that's 40 milliamps, and that already exceeds the current I can put through here. Plus, there's current from the other stages in the op amp as well. And so if we look here at these rails, you can see this rail's fixed at 2.5 volts. This rail here is nominally 6.5 volts, but the battery voltage. As the battery drops, this rail will come down, but this difference will stay fixed. And so the maximum output swing will come down as the battery decreases, but the thing works, and the automatic offset correction in the op amp keeps the input at 0. Now to the outside world, I'm free to call any node in the circuit ground because it's battery powered and it's not electrically connected anywhere to the outside world. So I'm going to call this node ground, or the low reference to the outside or the output. And I split up these resistors here on the output because these op amps can be unstable if they directly drive capacitance. And so these 24 ohm resistors, besides setting the output impedance of this, help stabilize the op amps if you hang capacitance out here or you go into a high impedance load with a long cable. So here's the whole circuit again, and here's a few key things we should look at. Well, first off, all the resistors are 5%. There's nothing special about them. R7 and R8, these two output resistors, are the only one where there's enough power dissipation to worry about, and they need to be at least 1/8 watt or larger. I've chose all the capacitors to be 16 volts or greater, so I have plenty of margin. And then when you build it, you have to be very careful about removing flux residue, because any flux residue, especially around these first 2 stages, can cause offset. And I had problems with that. After I built the second stage, I was getting this weird drifting offset, and I actually had to then flush the board in my ultrasonic tank with some isopropyl alcohol. And once I did that, then the output was stable again. So here's the breadboard. You can see the parts on the left, the top side, and here's the bottom. It's kind of messy because I was adding and removing parts and trying things. It's a breadboard. It's not a final version. And so here you can see the component placement. Here's the phototransistor, the feedback capacitor and resistor for the transimpedance stage, which are here. The first 2 op amp stages are U1, that's these 2 here. U2 is the output stage. C8 is the compensation capacitor for the output stage. D1 is the LED, and U3 is the band gap reference. Here we have the optical probe breadboard sitting on the bench, right here. You can see the phototransistor is inside this heat shrink, and this is flat black heat shrink, and I'm using it to make it more directional. Right now it's pointed straight up at my shop lights. If I put my hand over it, you can see that the signal goes away. However, you see seems to be what's an awful lot of noise on the signal. If I get my hand near it, you can see, it's very sensitive to pick up. You can see some signals here. Let's zoom in on the scope a little bit. So you can see that there's what appears to be quite a bit of noise on the signal. If I flip this over so it's pointing down, there's still an awful lot of noise. Get my hand near it. It's picking up stuff from the local radio stations and cell phone towers. But there's that just seems to be an awful lot of noise. And so let's see if it's coming from the circuit or from the external world. So let's back off here. So what I have here is a shielded box. The box, this is a conductive gasket around here, and it's got a little bit of echo zorb on the inside. But I can take this probe off, and so I can put it inside the box. We'll close the box off. I'll put this in here. That's good enough. I don't need to screw it down. It makes good contact. And we put this on the scope. And look, we still have a lot of noise coming out of this. So let's zoom in on the scope. Here. So this is what's coming out of the probe. It's now in a dark shielded box. So there's no interference coming in. So let's see what happens if we try and trigger on this. And let's move out. We see what appears to be some sort of noisy waveform there. And if we turn on averaging, choir, we'll let it go. And so this is coming out of the probe itself. And what this is input offset correction sampling. So the auto zero or zero drift op amps do this by sampling the offset at the input of the op amp or at the output and correcting for it at a certain frequency. In this case, it's about, let's measure it. It says it's about 300 kilohertz. Now this frequency varies a bit with temperature, and so let's talk about this some more. So let's talk about the offset correction sampling noise. The 300 kilohertz noise is a byproduct of the op amp's sampling input offset correction. It's primarily from the first transimpedance stage, but the second stage contributes a bit. And all zero drift op amps have it. The frequency and amplitude vary by op amp model, temperature, and circuit topology. And it doesn't matter in this case for very large signals, which will be fast, because it's going to be less than 1 LSB of the oscilloscope's 8-bit A to D converter. But for slower, let's say less than 10 kilohertz signals that are small, we can low pass filter it out. Now this is the same noise, but in my looking at it with the spectrum analyzer, and you can see here's the 300 kilohertz, here's the harmonics, here's some subharmonics. I think these other spikes here is noise coming from the other stages that's just not amplified as much, because there's no reason that this offset correction between the parts is going to be in sync. right? There's no reason at all that the various stages, that they all run independently. So now on the bench here I have one of my underwater flashlights pointing at the probe. I've got a piece of black heat shrink tubing over the phototransistor to protect it from the room light, so it's just seeing the light from the flashlight. And you can see here that I have a signal that's, let's put it here, that's above ground. So this is no light, and here's coming out, and there's some sort of glitch. This is on full brightness in there, that's probably due to the switching power supply in the light. So let's zoom in. So now watch as I change the brightness on the light. You can see here now I'm getting different, you see the brightness change in the signal, and you can see the scope change. Let me spread this out here. You can see here, this is full brightness, medium brightness, low brightness, full, medium, low. So let's go back to medium. And so you see these glitches here on the top of the waveform. I really think that's just the glitches coming from the internal switching power supply of this flashlight that aren't in sync with the modulation frequency. Now let's look at what kind of signal we got here. So this flashlight is actually modulating fairly fast, 31 kilohertz. And it's showing a rise time of less than a microsecond, and then but a slower decay time. I suspect this decay time is due to the phosphor. I think the LED turns off fast enough, but in GaN LEDs there's a phosphor that converts the UV or blue light into visible light, and that takes time to decay. So here, let's look closely at the medium brightness waveforms coming out of the flashlight. Notice here there's a little bit of underdamped response, and this was by my choice of that output compensation capacitor, because the amplifiers actually hit approaching slew rate and limiting, and by allowing a little bit of underdamped response there, I can keep the fast rise time. Now if we look at this decay, I know I said in the previous clip that it was from the phosphor in the LED, but I did some research, and the decay time of those phosphors are typically on the order of 400 nanoseconds, and this is much longer. So I think it's actually from the phototransistor, and the fact that when it gets to lower currents it doesn't respond as quickly as it does at higher currents. And over here on the right you can see when I put the persistence on, we can see that the glitches from the power supply in the flashlight that are out of sync with the modulation frequency. Yes. Although this probe has peak sensitivity in the visible, it still has limited sensitivity in the infrared. So if I take an infrared remote and put it right up to the control, I can read, you can see here, as I press buttons, I'm changing the pattern on the oscilloscope. So let's zoom in on the oscilloscope and see what's happening. So now as I press the buttons on the remote, you can see the oscilloscope change. Now let's zoom in on what's happening here. You can see these pulses are pretty fast. We're at 2 microseconds per division, and the probe is catching this. Let me do some more. So you can see that the sequence is lasting about 20 milliseconds. And interestingly enough, if you press the same button, the beginning of the sequence changes for each button press. But if I change the other button, so this is increase volume, this is decrease volume. So this probe's useful for looking at the data coming out of infrared remotes. Okay, so here we're looking at the amplifier. And so here you can see now if I put my hand over it, block it from the shop light, but it's looking up at my LED shop lights. And we have lots of noise. But what I can do now is I've created a low-pass filter. It's about a 9 kilohertz low-pass filter. And now we get a nice clean waveform because all the crap it's picking up is, along with the switching frequency of the op amp, is much higher than that. And so here, I block the light. And so that ripple we're seeing there is just the ripple coming from my shop lights. So this is the low-pass filter I built. And I picked these component values because I had them in stock. And I did some quick simulations, and it showed that it was going to be down about 40 dB at the switching frequency of the op amp, 300 kilohertz. If I were to redesign it, I might pick different values, but this worked well enough for this purpose. Now, if we look here, this is actually the shop light above my bench. It's a Braun shop light. And if we look over here at the waveform on the right, I put a blue line here. This is where no light is. And so here's the waveform coming out of the light. And so this is actually the flicker waveform from this LED shop light. Now here we have a very old fluorescent light. This magnifying lamp was probably about 20 years old when I bought it in the 70s. But I love it because the lens on it is wonderful. But it's just got a simple inductive ballast. Now I added the panovice here so it doesn't shake because any vibration shows up as the waveform moving. But if we look over here at the right, again, this blue light I added is zero light. We can see we're getting quite a bit more ripple out of this lamp than I was out of the LED shop light. And yes, the shop lights were turned off when I did this measurement. So with this probe, I'm actually very happy with my breadboard design, especially with the addition of the low-pass filter. And I will probably include that in a future spin of it. A good PC design will lower the susceptibility to electrical noise, but this is still going to need to be built into a shielded enclosure. The final design should incorporate a switchable low-pass filter as part of the probe. The PCB and enclosure do need to be designed together. And this seems like a good opportunity for me to learn KiCad, which I have never used, but I may use it for this project. Anyway, if you like this video, please give it a thumbs up. If you haven't subscribed and would like to see more videos from me, please subscribe. And if you have subscribed and want to be notified when I upload another video, please hit the notification icon. Thank you very much.